is the one, because this is IP, okay, and let me see, it's this. Okay. First, let me thank the organizers for the kind invitation. This is an interesting meeting, and so I will speak about wire relaxation. I will define it in a while, but first let me say that the original part that I'm showing you is a work that has been done with two students, Guido Giachetti and Alessandro Santini. Guido is now at Sissa, no longer in our university. And this is a content of pointer is this? No, there is. No. Okay. Then. This one. Okay. Thank you. Yes, it works. Now this paper, and then there are a couple of papers in preparation with also Alessandro. So I will be on the classical side, okay? So, and I will be speaking about classical particle system with long-range interactions, and I will stick only to what has been called recently the strong long-range regime. So when this the system is not additive and the pair potential is decaying at large distances slower than the dimension of the space. There are many physical examples of this kind of interactions. At the fundamental level, essentially, they are gravity and Coulomb interactions. So this interaction is very relevant to astrophysics and also, to some extent, to plasma physics, where there are the regimes where the Coulomb interaction is unscreened. And, but also in condensed matter, because we have seen that we have already been listening to talks about dipolar interactions that in 3D are in this class. And also there is this very interesting thing that I will not touch in my talk, but the fact that was just recalled by Nicolò in the introduction of his talk, that you can have effective long-range interactions that are actually mean field that is fully connected interactions that are mediated by the electromagnetic field in a cavity with the cold atoms. So this is another nice example. These are clearly quantum systems, but to some extent they can be treated semi-classically and so be close to the classical effect. The other point is that I will stick to the non-equilibrium part. And so if you want to know about equilibrium in the classical regime, I think you have to wait to Alessandro's talk. And so, okay, for this kind of systems, the out of equilibrium behavior is particularly important for an important reason. That is, okay, before let me just say that there is an important reference of that. We have the first author sitting here. There is Alessandro. There is this beautiful book. And also, two of the other authors should have been here, but for many reasons, they could not be here. So the book was almost fully represented here at the program, and then in the end, only Alessandro remained. So apart from that. Okay, so what happens in this kind of systems is that they very slowly relax to equilibrium. Okay? Their relaxation time not only is very slow, clearly saying that something is slow doesn't mean essentially anything if you don't compare it to some physical scale. But the important thing is not that the absolute value of the relaxation time to equilibrium. Is the fact that this time grows with the number of particles of the system. Okay. And so the larger the system is, the longer it takes to go to equilibrium. And I have to say that now, for me, and during all the talk, equilibrium will mean thermal equilibrium. So I'm not talking of equilibration in the sense that Michael Kastner was talking yesterday. That was even if then there will be some similar things at a certain point, but for me, equilibrium means the Boltzmann Gibbs. Okay. Okay, no, no, the example that I'm showing here, I wanted to say that this is was known already to Chandrasekhar for the self-gravitating systems, and then you can give an analytical estimate for any self-gravitating system that this relaxation time scale says n divided by log n. This log n is typical of the gravity. The gravity is special in many cases, but I'm not entering this technical point. No, this is just to the number. Because then no, but your question is very relevant since there is a debate whether there is or not dark matter. But at this level, it would only maybe change the numbers, may increase them. If you also have dark matter, just getting worse. There's not that so. So just to say that for this kind of systems, it's clear they're one of the most prominent examples of classical long-range interacting systems. There is obviously no way of seeing an equilibration because you have to wait many orders of magnitude more than the edge of the universe. So no way of that. Let me just say, as a suggestion from the question, I will be referring to the gravitational case for examples also afterwards. Gravity is special in some cases. There is not a real Boltzmann-Gibbs equilibrium defined. You have to do some technical things. But, so, and also for what I'm doing on the kinetics, there are some special issues. But they are not relevant for the qualitative picture that I'm going to. So, for the experts, I know that one should be more precise in the gravitational case, but this will not be. And then the results I'm going to show will be for the toy model that is not gravity. So there everything works. Okay. This said, since I don't know why it's a bit shifted, maybe we can. Maybe it's better. Yeah, now it looks like. Okay, so for the benefit of the young people here, maybe a very, very short primer on that may justify what happens in this system from the point of view of relaxation. I apologize to the experts in the audience that this is essentially textbook material, but just to have a common ground there. So consider a particle system, classical particle system, interacting via a pair potential. And then you would like to do a kinetic description. So you introduce one particle distribution function on your single particle phase space, and you ask how does it move in time. And you easily can derive an equation like this one, okay? And then here you have that there are two ingredients that you see. First, this part is due to the effect of all the particles. So there will be an effect, a mean field effect of all the particles on a single one, okay? And this is taken into account by this mean field potential. And then there will be the effect of the binary interaction. So clearly the distribution function will change also for the effect of the binary interaction that we could call, between many quotes, collisions, even if not necessarily they are collisions in the billiard sense, okay? And this depends on this. Clearly, you have to introduce the correlation function of two particles, but then at that point, clearly this equation is not closed. You have to put an equation for G2, and then this will couple to G3, and so on and so forth. And this is the well-known BBJKY hierarchy. Now, so if you want to solve the problem exactly, that's a big problem. But then you can do a sort of, you know, order of magnitude analysis and try to understand which are the roles of these two parts. So the interaction of one particle with all the others, and the interaction, the binary interactions. So it happens, it's quite easy to show that if you have short-range interactions, if you have that L, the capital L is the scale over which the distribution function is changing. R is the interaction range, and Xi is the correlation length, so the relevant scale of the G2. Then in the case that you have, in which you have only short-range interactions, you can see that essentially this term is negligible compared to that. So only this one, you can neglect this unless you have an external field, something that is imposed from outside. And then this is very complicated. But as most of you know, in the dilute case, you can express this in terms of F itself, and you end up with the usual Boltzmann collisional equation for the dilute gases. That is the usual thing. In the case of long-range interactions, it happens exactly the opposite. So what happens is that this collision part is completely negligible with respect to this. No? And it can be shown exactly how this goes. The ratio goes exactly this way. This was an old result, but it's been re-derived many times. So in the long-range interaction case, if you take the n to infinity limit, what remains is the so-called Vlasov equation, that is called also the collisionless Boltzmann equation, because it has exactly the structure of a Boltzmann equation, but without the collision term. And you see that the only interaction that remains is the mean field interaction. So this equation describes a dynamics that is purely mean field. So each particle interacts only with the mean field effect of all the others. Now, this is exact in the case when n goes to infinity, but, and that's important, essentially this describes the dynamics also of finite system, provided you don't want to take too large times. Okay? If you remain below the relaxation time, then still the dynamics is described. So at a certain point, you have just a finite horizon. At a certain point, a collisional effect will set in, and so the dynamics will become completely different. But up to a certain point, it doesn't make a big difference whether your system is really in the n to infinity limit or is finite, clearly large n. Otherwise, this is okay. Now, this equation has a lot of very interesting problems. Again, this is going, so I'm putting my hand on. I think it's full screen, yes? But yeah, but I can correct adiabatically. Okay, so it has a Hamiltonian structure, this equation, and this is a very nice property. So you have to have a Herschel invariant and all this. It is a very strange kinetic equation, if you want, because it's not a real kinetic equation in the usual sense, no? Because you have no collision, so it's not really kinetic. It's something, you know that any function that is a function of the integral of motion of this Hamiltonian, that is the effective single particle Hamiltonian, is a stationary solution of this equation. And clearly, for instance, the Boltzmann-Gibbs equilibrium is a stationary solution, but it's just one out of the other. There is no special role of the Boltzmann-Gibbs equilibrium among all the infinite possible functions of the Hamiltonian that you can derive. So, and then there are other constraints on the Vlasov dynamics, that there are infinitely many conserved quantities that are called the Casimirs, usually, that you take any, reasonably well-behaved function of the distribution function, you integrate it over the single particle phase space, and you get this number. This is a constant of motion. So it's a highly constrained dynamics. The important example that again tells you that there is no special role of the thermal equilibrium is that one of the Casimirs clearly happens to be the Boltzmann entropy. So this quantity is a constant of motion, doesn't grow. During the evolution, there is no H theorem for the Vlasov dynamics. So what happens, what kind of dynamics is described by this equation? Obviously, we won't be surprised that it depends on the initial conditions, clearly. But the interesting thing is that does not depend in a naive way. So let's first speak about the obvious case. You may happen to start with a solution. Now, in this case, I'm considering a system that is large by the finite n. Okay, so what happens? If you start with the initial condition that is a stable stationary solution of your Vlasov equation, obviously you stay there until at a certain point your description breaks down because the time has gone sufficiently on to make collisional effects relevant. And then your system at that point will relax to the usual Boltzmann-Gibbs equilibrium, okay, if it's defined. So for gravity it's a bit different. But the very interesting part, and now we arrive to the title, at the title of the talk, is what happens when you start with a generic initial state that typically will not be a stable equilibrium of your equation. And at this point, what happens is a very strange thing, is that the dynamics is essentially two-staged. So you have a first part of the dynamics that is fast in the sense that its time scale does not depend on the number of particles. That just depends on intrinsic time scales of your system. And on this time scale, the distribution function has rapid changes. And this phase was termed violent relaxation by Lindenberg. That was the first one who studied these problems in the gravitational context. And what happens is then your dynamics, if you look at given observable, seems to get trapped in a state that is typically called a non-equilibrium quasi-stationary state that is, in general, completely different from thermal equilibrium, but looks essentially stationary. Okay. So again, if you then wait long enough, you will have the relaxation to equilibrium, to standard equilibrium. Okay. But this long enough always will, very often will be too much for any accessible scale. So if you want to, make a summary of what's going on, you see that given initial conditions, you have first the violent relaxation. This leads you to a quasi-stationary state. You stay there if the system is large, essentially forever. At a certain point, you will see relaxation to equilibrium. Okay. Now, there are clearly many open questions concerning this. Clearly, the violent relaxation then becomes the most important phenomenon in many relevant physical cases, because the only thing that you may think to observe is this stationary state. Clearly, this one typically is so far away that there is no possibility of seeing that. To go back to the gravitational case that I was using as an example, we think that the galaxies are in this state. Clearly, they are not in the analogous of the thermal state for gravity that would be the real end state, because they didn't have time to go there. Okay, so just to give the typical example, again, that is a gravitational collapse, you take a bunch of self-gravitating particles, you put them in an almost uniform configuration. It clearly is absolutely not a stationary solution of the gravitational case. You let them go, and what you see that depending on the initial conditions, and I'll explain what, the first experiments were done by Anon, but then this is a recent, more modern case, but nothing really changed from the point of view of qualitative point of view. You see, this is the gravitational radius that is essentially a typical scale. In the system, you see that clearly the system collapses. And if the virial, this is the so-called cold case. So if you have no kinetic energy, your system rapidly collapses, and then it has small oscillations, and then goes into the quasi-stationary state. The same happens if your system is warm. Oscillations are damped on the longer time scale, but it's the same thing. So, a lot of open questions. I'm putting them in a naive way, but clearly that can be just to set the stage. Now, clearly there is a problem. So you have something that is a non-real kinetic equation because it doesn't have a collision term, doesn't break the time reversal invariance, but it has to describe what looks like a relaxational process. Now, naively one can say, how could it be? We know that there are a lot of examples of this kind. It's not, but what is probably the most relevant? Well, another one that is described just by the Vlasov equation, that is the Landau damping in plasmas, because it's very similar as a phenomenon. But the problem which is that the usual way, this is a problem that has been solved by Landau himself, so it's an old problem. But the problem is that the solution is, between quotes, easy, after Landau did, in the linear and homogeneous case. Linear means that you have to perturb your system by a very small amount. And non-homogeneous means that your state you are perturbing has to be homogeneous, spatially homogeneous. Now, in this case, the problem becomes completely linear. You can solve it, and there is a beautiful Landau solution that explains you how it's possible that your system seems to relax even if there is no relaxational dynamics there. The problem is that clearly the idea is that this is what happens also in this case, but you have to do it in non-homogeneous and non-linear case. And this is awfully difficult. It's really a tough problem. In the case of a model that is the one that I will be using afterwards, this problem has been attached in a series of papers by Julien Barré and Adriano Olivetti and Yoshi Yamaguchi, I think, if I remember well, the third author. And they derived a lot of interesting results, but couldn't solve the problem completely in the case. Very, very nice papers, by the way. Really, what is that happens during this violent only? So I was too fast, too slow in the introduction. Then I will. Okay, let me just say. Let me just go to the results are fast. So okay, the other problem that remains open clearly is to understand which is the state that is selected after this process. And there are some approaches, but again, the problem is not. So we decided to attack this problem on the famous HMF model that has been the workhorse of this area for many years. And that is essentially a fully connected XY model or a model of particles on a circle. You can look it the way you prefer. If you take symmetric initial conditions, you simplify the description and without losing generality, and the Vlasov equation becomes this one. If you look at the cold collapse, like in a gravitational case, you see essentially the same thing if you look at the magnetization of this system of spins. So you have these oscillations that typically are termed virial oscillation due to the gravity jargon, and you see that they are damped again. Now, to try to solve this problem, what we did was to introduce a coarse graining this way. That is, you take moments of the distribution function as variables, so you can write a truncated evolution equations for these moments instead of an equation for the distribution function itself. You can write it down, not important. What does it mean? This equation shows you that the low-order moments interact among themselves, while they force the higher-order moments, which then react back with what we think is the origin of this damping of the oscillations. So the simplest thing you can do is you just truncate at the lowest order, and this it can be easily shown that it reduces to a Hamiltonian dynamics for a variable that is tightly connected to the magnetization, and so in an effective potential that is nonlinear but is a well-usual one. And then, so this describes the virial oscillations, but not the damping, because clearly this is conservative and nothing. But if you simply assume that for some reason there is damping, you can make a prediction of where your system goes in a quasi-stationary state. This is the theoretical prediction. These are the simulations. Not so good, but not even completely out. But the interesting thing is that that one can actually derive the effective dissipation. How? The idea is to use the same kind of approach that was used by Caldera and Leggett to model open quantum systems. That is, all the higher order moments, with respect to the low order one that were included in that previous description, are treated as harmonic oscillators. And then you apply all the machinery. That is tedious, but it is a slight variation on their calculation, but not really much different. And then you end up with two interesting results. First, you derive dissipation, exactly as they did. But there is a difference with respect to that. We also have a renormalization of the effective potential. Two numbers come out. Since this is a renormalization procedure, you can't calculate them. It's like when you dress the electron, no? So it ends up with a number that it is a free parameter of the theory. But the theory works only if this is small, compared to the units that now are 1. Everything is scaled to 1. And so what's going on now? If you choose the right number, this result depends only on one of these constants. You see that things work very well. So in this case, it seems that this effective theory works. Just you can go to higher orders and things go better, clearly, even if you can no longer do this nice trick of doing analytically the dissipation. You have to put it at least, no, it's not you can't, we couldn't. Maybe someone else is able to, but we couldn't. And if I have a flash on the final, yeah, a short flash is just this, that all this was for the HMF model and very adapted on that case. So, but it turns out, and this is what we are publishing in a while, I hope, that you can write something very similar also in the general case. So you can write an effective equation at this point for a coarse-grained distribution function that has a zero-order operator like this oscillation, then a series of operators that describe a renormalization of this part because there are invariant anti-remerge, and another series of operators that instead describe the damping. And you can, this can be constrained by symmetry arguments, and in the case of 1D system, you can compute that explicitly. You can make a prediction, and this prediction for the HMF is verified. So we believe that. And I leave you the conclusions, and sorry for being a bit long.
Let's have, say, 2 questions, please. Who want to be first?